Okay, so we have a question here. It's question 8. It's from a physical sciences paper 1. This was for grade 11, right? Cool. And let us just read the question. The question says two identical point charges. So we have x and y, which are identical, are placed 2 millimeter apart. So the distance between x and y is 2 millimeters, right? Cool. So please try to jot down the question, because I'm not going to bring it up again later in the lesson. And then they mentioned that point P, there's a point P here. They've shown you point P is 3 millimeters to the right of the charge Y, right? Cool. And then you can see that this point is 3 millimeters away from point Y, from charge Y. And then they give us the net. It's the net electric field at point P, right? Cool. And then that they say that the net electric field at point P here. So the electric field, the net electric field, is the electric field that this point P experiences because of both Y and X, right? And they saying that that net is 5,44 multiplied by 10 to the power of 6 Newton per coulomb, right? To the left. An important thing, because electric field strength is a vector. The electric field, so it's a vector. It means that you must provide its magnitude, which is 5.44 multiplied by 10 to the power of 10 to the 6, and then also the direction to the left, right? Cool. So now question 1 says to us, define the term electric field at a point. You should know this definition by now. And I'm going to mention its definition again later when we're actually doing the question. But you should know that electric field at a point is the electrostatic force per unit positive charge placed at that point. But we will talk about it again later. Let us just read all the questions. And then 8.2 says to us, are the charges negative or positive? So charge X and Y, we know they're identical, so they have the same sign. They can either both be positive or both be negative. So the question is asking you, are they negative or positive? It's an interesting question, and you'll see how we go about answering it, right? And then 8.3 says to us, we must draw the resultant electric field pattern for those two charges X and Y, right? And then 8.4, we must calculate the magnitude of the charge X. We must find out what the charge X is, its magnitude in coulombs, right? It's 5 marks. It's going to be a very interesting question, you'll see. And then the last question says that charge Y is now replaced by an identical oppositely charged point charge, right? Cool. And now it's asking us, how will the magnitude of the net electric field at point P be affected? Remember that net electric field was 5.44 multiplied by 10 to the power of 6, if I'm not mistaken, right? And now if we change the sign of this, how will it be affected? Will it decrease, will it increase, or remain the same? And you must provide a reason. So you'll get a mark for saying increase, decrease, or remain the same, and then you get another mark for providing a reason. So let us just get straight into it, right? This is the setup that we are given, right? So we have point X and Y, which are 2 millimeters apart. So the distance between them is 2 millimeters. We know milli means 10 to the power of -3. So we can just write this as 2 multiplied by 10 to the power of -3 meters, right? Cool. And now we also have a point here, a point charge, a point actually. And the distance between this point and the charge Y, they said it is 3 millimeters. Again, we know milli means 10 to the power of -3. So we'll actually have 3 multiplied by 10 to the power of -3 meters. Because when we're doing calculations, we actually have to substitute in our formula the distance in meters, not in millimeters, right? Cool. And then what's the other important thing? Now we have to also find, if the distance between this and this is 2 and the distance between this and this is 3, what is the distance between X and this point P over there? We can know that it's 2 plus 3 millimeters, which is 5 millimeters, right? But however, we know that milli again means to the power of 10 minus 3 meters, right? Cool. So the distance between X and P is 5 multiplied by 10 to the power of minus 3 meters. You'll see why it was important for me to kind of write down all of this a bit later on. So before going to answer our questions, we also have to say, okay, what is it that is given to us? We are told that the charge we represented with the symbol Q. So the charge on X is identical to the charge on Y, both in magnitude and also in terms of their signs, right? So let us just call it charge Q. They are equal in magnitude as well as their sign. So they can either both be positive or both be negative, right? I'm trying to figure out the last thing. And then we are told that at this point here, the electric field, the net electric field at P, so this is at P, is equals to 5.44 multiplied by 10 to the power of 6 Newton per Coulomb, right? That is what they told us. That is the information we know already, without having done any sort of calculations. And then we had question 1. Question 1 wanted us to state the term electric field. So the electric field at a point is defined as the electrostatic force per unit positive charge. It's very important. This is an important thing, per unit positive charge placed at that point. So the electric field at this point will be the electrostatic force per unit positive charge. It means that we kind of have to assume that this point here is a positive charge, right? It's going to be important when we're doing the calculation, especially in terms of determining whether our charges are negative or positive, right? So now they are saying to us 8.2, right? 8.2 was saying to us, are those two charges, X and Y, both positive or both negative, right? How do we go about answering that? Think about it. So we know they're identical. So we know that X and Y are identical. So they can either both be positively charged or they can either both be negatively charged, right? And now we have a point here. This point here experiences an electric field. And they said per unit positive charge placed at that point. So we have to assume that that point is like a positive charge, carries a sort of a positive charge. Unless it's stated otherwise, you assume that it's carrying a positive charge, right? And they said to us that the net electric field strength that this charge experiences is 5.44 multiplied by 10 to the 6 Newton per Coulomb, and they said to the left. So it means, so we can say, okay, this direction is to the right, and then this direction is to the left. So it means this charge is moving to the left. So now let us think. If this charge is moving to the left, so we know that if this charge is positive, and this is also positive, it means there's a huge net positivity over here, and we know that positive and positive will repel each other. In which direction will this point move? It will move to the right because it will be pushed away because of this positive, right? It will be pushed away. However, if both these two things are now negative, remember our charge, we're still assuming that it's positive. Our point, we're still assuming that it's positive, right? If it's negative, what will happen? This charge will actually be attracted. So it will move to the left. So if this charge is moving to the left, it means that both these two charges are actually negative. I'm hoping you were able to follow my logic, right? Cool. And then we are now required to draw the 8.3. You have to know also how to draw this electric field patterns, for charges. I think it's something that they teach you. So how you normally draw it, so we have to draw this electric field patterns for these two charges x and y. So normally you would just draw a circle to represent your charge, right? So we said both of them are negative. So inside that circle, you draw a negative thing. And we know that the electric field lines will always point towards the negative, right? It's almost like they're pointing that it coming into the negative. If it was positive, remember, it would actually be away. But in this instant, it's actually positive, right? So it's negative. I'm sorry for that. So you draw them, but you make sure that you draw them nicer than I am drawing it. And then because these two charges are actually negative, both negative, the force of the force between them is repulsion. They are trying to push each other away. So I'm no longer gonna draw straight lines. My lines are gonna bend a little bit because they are sort of pushing each other away. They don't want to be in each other's space, right? They are repelling each other. So you will draw those lines like that. Check in your books to see how you actually draw these two configurations. You have to be able to draw these electric field patterns for charges that are both positive, right? Charges that are both negative, and charges that are positive and negative, right? So make sure you check in your book how to actually go about doing that. And then the interesting question that we're gonna do now is the question that required us to calculate the magnitude of the charge x. So let us try. I'm gonna wipe my board quickly and then we can go about solving it. Right. So we were given that so we had point, I don't know why I removed them, so x and y and then p there to be our charges, right? Cool. So we were told that the net electric field at this point here was 5.44 multiplied by 10 to the power of 6 Newton per coulomb, right? To the left. Cool. So when something mentions net, it should or almost instantly click to you that you adding all the contributions. So in this instance, we have two contributions. We have, so E net, we will add all the contributions by, so we add the electron, so we'll add the electric field due to point X on P, right? So we'll have E on P because of X, right? And then the second contribution that we'll have will be the electric field on P due to the presence of Y. So you'll have E on P due to the presence of Y. If we had another charge there, we'll also add that contribution. So that's what net means. We are adding all the individual contributions. Same thing when we talk about F net, you add all the forces that are essentially acting on your object. Here you also add all the electric fields that are essentially having an effect on P, right? Because this charge has any contribution on P as well as discharge. So we'll add all of them together. And we should know that from our formula. We have this, so we don't worry too much about it. Our formula, which is given to you at the back of your question paper, will tell you that electric field strength is given by E, right? Which is KQ over R squared, right? So it's a formula that you should be familiar with. So we will write it down. We will say, okay, electric field on P due to X is E is going to be K, our charge X divided by R squared, but it's the separation between them. Remember the distance between X and P. So it will be the distance between X and P. So hence I write XP there to remind me. Plus now K, Q, Y now, and then R squared and then the distance between y and p, right? Cool. But now I said earlier that the charge q and the charge x and y are the same. So I said we can just assume it's okay. So qx equals to qy. So we can just assume that it's q. I'm going to write it down as q because it's the same charge, right? So essentially I will just write k q over r squared xp plus k q over r squared yp, right? Cool. And now this is just, I'm gonna do a little on this side. We still have E net, right? E net, net electric field, right? So, and then it's just a matter of math. I'm going to take my q out as a common factor. When I take it, we are just left with k over r squared xp plus k over r squared yp, right? And on this side, I have E net. So you'll know that I'm looking for this. This is the variable, the quantity that I'm looking for. K is given to us at the back of your question paper. It's a constant, right? It's Coulomb's constant. And then you also know the distance between x and p. We said it's 5 millimeters. You know the distance between y and p. We said it's 3 millimeters, right? Cool. So now I can just try to make x my subject. It means I'll divide both sides by the entire bracket. So if I divide both sides by the entire bracket, you'll find that q is just going to be E net, all of it divided by, I hope you can see, right? So E net, all of it divided by k over r squared xp plus k over r squared xyp, right? Cool. And now it's just a matter of substituting everything. So we know E net is 5.44 multiplied by 10 to the power of 6. So it's very important for you to here to be able to know to use your calculator, right? Otherwise you're going to get the wrong answer. And then we have 9. So this value is a constant. Its value is 9 multiplied by 10 to the power of 9. And then the distance between x and p, we said it is 5 millimeters. So it's 5 multiplied by 10 to the power of minus 3 meters. And all of it is squared. Plus, right? So you get a mark there. And then you'll have 9 multiplied by 10. All of it divided. The distance between y and p is 3. So we'll have 3 multiplied by 10 to the power of minus 3. All of it squared, right? Okay, there was no need to include this bracket over there. And now your task is simply to just put this in your calculator. And if you do that, you'll come to a number 0, 0, 0. Have a lot of zeros. I think a 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll come to a number like this. So you can write it in short notation or scientific notation, say 4 multiplied by 10 to the power of minus 9 coulomb. Or we can just write it, someone who say 4 nano coulomb. You know that nano means 10 to the power of minus 9, right? Cool. So the last question, hopefully everything was clear in terms of how actually we determine the magnitude of our charge. So therefore the magnitude of our charge is 4 multiplied by 10 to the power of minus 9 coulombs, right? And then let us try to answer the last question quickly. So the last question is basically telling us that we have two charges, x and y, right? Initially, we determined that both of them were both negative, right? Now they're saying that we changed it's still identical, so they still have the same magnitude, but now this one is replaced with a positive charge. So now we have point P, and we had said that the electric field that it experiences there as a result of the presence of x and y is 5.44 multiplied by 10 to the power of 9 Newton per coulomb, right? Cool. So they're asking us, when we change the sign of y, will this value increase, decrease, or just stay the same? What do you think? What do you think will happen? So I think it's almost intuitive for you to realize that that value will essentially decrease, right? But why will it decrease? Try to think about it for a little while. So so when when now these two charges have are oppositely charged, right? It means that um the electric field their electric field will now be in opposite direction, right? And I want you to think about this. If you have a friend, you guys are pulling on a rock. So you pulling at a rock at 2 newtons, a force of 2 newtons. She's also pulling at this rock at a force of 2 newtons. It's almost as if you guys in total, your F net, let's consider that there were no other forces. So your F net will be 4 newtons. So almost like you actually pulling this entire rock, or the rock will almost seem like it's being pulled at a total force of 4 newtons, right? So your individual contributions are added because you guys are pulling in the same direction, right? Cool. Now, what happens when you pulling at 2, and now somebody else there is pulling at 1 newton, is pulling in the opposite direction? You will sort of cancel each other. It will almost be as if this rock is being pulled, its F net is being pulled in this direction at a force of 1, because we just say 2 minus 1, right? So when now the electric field are in opposite directions, it means that it will decrease for exactly the same reason, because electric field, like force, is a vector quantity. So the electric field being a vector will decrease because of the opposite directions. Because now they are in opposite directions, their net effect is decreased. If they were both pulling the same directions, the net effect will be increased. Hopefully that is clear, right? So yeah, we can definitely end this lesson. I hope this video was somewhat helpful.